Good morning, everyone. Good early morning. So welcome to the special DPF session on the CDF W mass measurement. So many of us, my name is Tao Han, the DPF past chair, and I'm co-chair on this session with Untitled DPF vice chair. So many of you must have heard the announcement last Friday, and the CDF made a new analysis, quadrupled the previous data, and reached the extremely high precision for the leptonic measurements for the W mass. They shrink the error bar by factor 2 and literally leave a significant difference from the global fit for the W mass and also the other standard model parameters. So that may carry very, very important implication for us to understand the standard model as well as understand the possible new physics beyond standard model. So I'm very grateful to the APS meeting today, and with such a short notice, they pull out together to form this additional session this morning. To make this session more memorable, we make this at 7 o'clock, 4 o'clock Western time.
Thank you.
So today we have a distinguished panel for this session. So we have 5 members for CDF, Ashutosh Kalwal, and he was the primary leader to conduct this analysis. So he's going to give us the presentation about 40 minutes. And after that, we have CDF co-spokespersons, Giorgio Chiarati and David Toback, to join us for discussions. And also we have Christoph Hayes as the electric physics coordinator, as well as Bo Jyotilaka. He served as a primary analysis as well. So with that, I think we should get started. Hopefully, we will keep all the discussions on time and leave plenty of time for questions and answers. Okay. So on that note, I would like to once again congratulate the CDF to achieve such monumental measurements. Okay. So Caldwell, so please take it away.
Thank you, Tao, and thank you all for coming early. Should I share my screen and go ahead?
Yes. Yes.
All right, thank you. 1 second. When I share screen, it is asking whether I should leave the breakout room, which worries me. Now, somebody confirm you can see the screen? Yes, all right. All right, thank you again, everybody, for this opportunity on behalf of the CDF collaboration to tell you about our recent publication as of last Friday on the high precision measurement of the W Boson mass with the full run-2 data set. I just want to flash this picture. It shows an opened up version of the CDF detector. You can see the beam pipe. This large 2.5 diameter circle here is our central drift chamber, which plays a crucial role in the analysis. Surrounding that drift chamber is an EM calorimeter, which also is extremely important for the electron channel. And surrounding that is the hadronic calorimeter. So very briefly, we understand, all of us, the motivation for making precision measurements. I'll say very briefly why MW is one of the precision measurement quantities that we've always wanted to make more and more precise, what sensitivity it might have to new physics. Most of the time that we have here, I'll spend on describing how the analysis is constructed, what are the primary driving philosophies behind the choices we have made, which high precision cross checks we have built into the analysis. I will then describe the experimental apparatus very briefly, and within the time we have, show you as much of our data as possible. These distributions will be all taken from the publication, and I will mention that along with the 7-page paper in Science, there is also about 50 pages of supplemental material which describes in as much detail as possible the cross checks and the techniques that we have used. So with that, the standard model, we all know, is a magnificent theory with many theoretical axioms and built into it. Along with those, there are some parameters in the model, and those parameters can be constrained by some very high precision measurements of other quantities. The important ones for MW calculation, for example, are listed here. With the 2012 discovery and subsequent high precision measurement of the mass of the Higgs, now the model in some senses is self-consistent and complete. So there is not that much wiggle room in that for predicting high precision measurables like MW. So at tree level, we know this is a relation that the standard model has. We have been able to go beyond tree level for a very long time. So the fluctuations in the W boson propagator due to, for example, top and bottom loop, Higgs loops, these initially were the targets. So by making MW more and more precise, historically one could infer what the top mass would be. Then later it became a way to infer what the Higgs mass might be. But now having all of those very well known, it becomes a way potentially to infer if there are other new undiscovered principles or particles participating in those loops. So the precision with which the global data sets and the standard model put together is able to calculate or produce an expectation value of MW. This is the value in the literature. The uncertainty coming from the input parameter measurement uncertainties and the higher order theoretical uncertainties due to missing loops, for example. Both of them are rather small and roughly equal to each other. So this is the target that one wants to compare to and see what one might infer from the comparison to the measurement. So many ideas have already existed, and we mentioned a few of these as the introduction to our paper before we launched into all the experimental details. Just flashing one here, a paper that discusses a singlet, which means it has no standard model charges, but otherwise it is a scalar, so that one can mix with the Higgs boson that we know about that has been discovered at the LHC. So there is a mixing parameter here, and there is a mass for this other scalar particle. And as a function of those two, this particular paper describes calculated deviations to the MW compared to the standard model expectation. Okay, and the other favorite that has been there for a long time is supersymmetry. So there have been very significant exclusions in the parameter space of SUSY from the LHC, but it is acknowledged that that is a multidimensional parameter space. So it is possible that there are still some possibilities open where some of these contributions might still come in to the loops involving the W boson. Okay, and then moving to a sort of historical perspective randomly chosen before the start of run 2. So we have about 9 inverse femtobarns from the run 2 data. Before the start of that, run 1 measurements and LEP measurements were coming along. So this was the status, and that's what we have been trying to do for 20 years, improving measurements, both at LEP, Tevatron, and of course the LHC as well now. Here is one more parameterization of new physics. This one is called the well-known STU parameterization, and it involves calculations of new physics contributions specifically to the self-energies of the W and Z bosons. So one thing I would say in the space of S and T, typically U equal to 0, there are reasons why that is likely to be small compared to S and T, but it is worth mentioning that MW is one of the perhaps unique observables in precision physics, which is actually sensitive to the third one, to the U parameter as well. Okay, so to set the stage for this particular result that we published, this is a table on the transverse mass fits. So this is one of the kinematic quantity that has information on the mass of the W boson. Typically, for a long time now, one has always been thinking which of the uncertainties could be strongly constrained by the collider data themselves, if the model can be defended and shown to be robust. So the green ones were historically heavily data constrained. So one might say, as more data were added, that those uncertainties could go down. So we will see, and you will see that that indeed has happened. The black ones are a mix of systematic variations within the data, and higher statistics of the data, so classified somewhat differently. And then the red ones are the two sources of uncertainties where external information is the dominant source of information that we take from the entire community. Proton structure, calculations that incorporate the proton structure into functions that become inputs to the calculation, parton distribution functions, and of course radiative corrections, which is a purely theoretical exercise. So, describing how W boson production would look at the tevatron or at the LHC, for instance, also, here is a transverse cross-section of a generic detector. So you have the W boson decaying to a clean electron or a muon. So that's the one that is selected so that you make the momentum measurement of the lepton very, very precisely. Most of the complications in the analysis come about from the fact that the neutrino has to be inferred. So even though it's a two-body decay, you really only see one of them. So the other part of the event, which is the hadronic activity bouncing off or recoiling off the W due to all kinds of initial state radiation, that also has to be measured with some precision. So one of the advantages of the tevatron is the quarks on the proton and the antiquarks on the antiproton. About 80% of the cross-section comes from valence-valence collisions. So that is somewhat of an advantage because those are the parton distributions which are relatively more precise than antiquarks or gluons. So the goal becomes whatever precision one is shooting for, it is necessary to measure the lepton with that precision. So you will see we have achieved 0.004% precision on the lepton momentum. The hadronic activity is much more difficult, but the requirement on how precisely you can calibrate that is also smaller. So 0.2% is achieved here, and that leads to sort of commensurate uncertainties between the two sources of energy measurements. Okay. A brief picture of the drift chamber shown here, which is the source of our absolute momentum calibration. And that has been one of our design philosophies, that the analysis will always be anchored off the energy calibration and momentum calibration from the drift chamber from first principles. This is then transferred to the EM calorimeter using the electrons from W and Z decays. Then the hadronic calorimeter and any other activity in the EM calorimeter, that is calibrated assuming transverse momentum balance in Z boson decays. Okay. And this is an actual photograph where the end plug has been removed and the silicon detector, I believe, is being inserted at the beginning of our end. So the goal for event selection, we want events with high PT leptons. Those are the ones close to the Jacobian edge coming off the W. And in order for the Jacobian edge to be not smeared out by the transverse momentum of the W, one can require the hadronic activity to be small, and that means less than 15 GeV in transverse momentum net. So relatively simple requirements that do not bias the selection and therefore do not potentially induce some bias in the kinematic distributions we will be fitting. It is a pretty good combination of requirements that is preventing this kind of bias from coming in, and yet the efficiency is very high and the backgrounds are rather low. So this works quite nicely. Here are the sample of events we have. About 4 million in the W channels, electron and muon, roughly half and half each. And you see the number of events in the Z bosons for electron and muon channels. And it's often noticeable why the rates are like this. And a quick explanation is this is completely because of the fiduciality requirements, which regions we are excluding from the detector because the instrumentation there is not as high quality as we need. So the combination of double such requirements from the electrons versus the muons and so on results in this particular pattern of event distribution. Okay. Data set collected over 9 years from 2002 when physics running was declared up to the end of the tevatron, September 2011. About 9 another center ones. Okay. So driving goals or driving philosophies. First one is robustness, which means all the important parameters that one wants to constrain in order to achieve that precision. To the extent possible, try to keep all options open, which means be able to measure that parameter or those parameters in as many different ways as possible. If the consistency can be demonstrated, then that builds the confidence that indeed the parameter is being, showing itself in the analysis in every different way as a self-consistent number, for example. Once the robustness is demonstrated, then one can make the argument that those independent measurements can be combined. So we will do this whenever we demonstrate this. So that helps to increase the precision because indeed, as you will see, for example, the J size and the epsilons show up as consistent measurements of the momentum scale, so we can combine them. Last driving philosophy, analysis always requires decisions. So we want to be disconnected from the actual values of important things like the Z boson mass and the W boson mass. So there is a blinding strategy that has been published. It's the same strategy that we have been using for every publication in RN2. And I would emphasize that along with blinding MW, MZ is treated by us as an important demonstration that the momentum scale is well understood. So that one is also blinded separately from the W, but combined electron and muon channel have the same blinding offset. So as you probably know, there was a day when the analysis was declared final and then MW was unblinded. Similarly, there was a day when the momentum scale was declared final and the Z boson mass was unblinded. Starting with the calibration of the tracker. So it's a beautiful device, 30,000 sense wires. Spend a few minutes just showing you the alignment efforts going into the tracker, which then allows us to say, we will use the J size and the epsilons to calibrate the let's say the magnetic field of the tracker, the amount of material, passive material in the tracker, which produces a small non-linearity that we can see. This then allows us to say, let's check if the Z boson mass a priori comes out right, independent of any input from the world average Z boson mass. You can then analyze the electron channel similarly by using the tracks as a calibration source, sort of a test beam in situ, where you have the electrons from the Ws and Zs themselves to calibrate the EM calibrator. Then you can ask the same question for the Z boson mass in the electron channel. Does it come out right? All of these distributions involve peaks. So peaking distributions always give you a very nice way to constrain resolutions as well. These are ultimately rather small sources of systematic. I will then discuss in the time possible, just flash some distributions of the data showing how the hadronic recoil calibration is working out, and it works pretty well. And the basic philosophy there is transverse momentum balance in Z boson events. Okay. So a picture of the drift chamber. This is the end plate. It's a thick aluminum plate, 2.5 meters in diameter, with these slots cut into it where the wires are installed. So 30,000 wires are going from one end of this cylinder to the other, which is roughly a distance of 3 meters. Okay. So there was a technique we were developing for almost 20 years now to use the cosmic rays coming down from the sky. These provide a beautiful sort of reference fit with respect to which you can line up all the sensors in the drift chamber. And a special tracking algorithm was written so that you could reconstruct the entire cosmic ray trajectory from both sides. The tracking for collider tracks, of course, is just from the middle to the outside. So a somewhat different algorithm was used here, including the fact that the drift chamber timing is important because the timing of the cosmic ray is completely asynchronous with the beam crossing. But all of these data were taken during beam running. So it really is sort of in situ cosmic ray data, not when the tevatron is off. So it is exactly the same running conditions. Okay. A couple of plots showing a priori from the survey of the wires, what kind of precision was achieved on the alignment. So this is about 50 microns that you can see with this technique. So pretty good at the alignment level from a priori surveys. But then with this particular technique, that has been collapsed down to sort of 1 micron precision. You can see the y-axis is significantly smaller now, from 200 microns to 10 microns. So this is just one slice. X-axis is the azimuth, and it's a particular radius at which the wires are being shown. And this is done for all the wires in the drift chamber. This is a sanity check, which is you can now break up the cosmic ray back into its 2 halves and check that the 2 halves of the drift chamber are giving the same answer. So that means if the check is right, then the answer comes out near 0. So these distributions ought to be near 0 and symmetric and Gaussian and so forth. And indeed, that's what we see now. Many iterations were performed. So for every analysis, this particular technique was improved. And for this analysis, there was a separate publication that describes all the details. The 5 distributions here are the spatial parameters of the track. The 6th one is a timing parameter. And that particular histogram can then be shown as a function of azimuth or polar angle. So just showing you that it's not just the average that works out, but as a function of where you are in the drift chamber, it is also working very well. So with that, it allows us to make a following claim, that the measured curvature, so it's a tracker, so it measures track curvature, becomes an analytic smooth function of the curvature that you're trying to measure. So this is the true curvature, this is the measured. This is so-called false curvature, so that's the one that dominates any misalignment effects at high momentum when PT goes to 0. There is a constraint on that coming from collider data, which is very powerful. It would affect positrons and electrons in opposite directions. So this is an open technique. It has been used for decades, that you use the ratio of electron energy to track momentum, differentiate between positrons and electrons, and look at the difference. So the C0 term becomes extremely small, almost 0 from the cosmic ray alignment, but a small tweak is needed, which we get from the actual in situ collider data. So I don't want to put all the decimals here because indeed, to the numerical accuracy we care about, it really is 0. So from this point on, we'll be constraining the C1 and the C2. Before going to the J size and epsilon fits, overall, it's a detailed calculation using production model, detector modeling, QED radiation, everything one can think of goes into a customized calculation, which is fast, but it includes all the first principles knowledge that we can possibly think of. So that calculation is then able to produce distributions of any kinematic quantity one would like, such as the ones containing MW information, the PT of the charged lepton, or the neutrino, or the best combination, which is this quantity called transverse mass. So as is well known, we just make templates, standard technique here, where MW is scanned from over some range in very small steps. And this is an illustration how the distribution would change. You would then use a maximum likelihood fitting technique to the data to extract the mass value. So there has been some discussion about this. We will just say for now that we have continued to use the Resbos calculation that CDF and D0 have had significant experience with. And with all the distributions we have been checking, this calculation is giving us the ability to describe the data very well. So it includes resummation and next leading order, fixed order calculations. Initial state radiation is included. Final state photon radiation is not included. So that was interfaced with the program called PHOTOS, another well-known program. So just going to PHOTOS for starters, we looked at comparisons to another more inclusive calculation called HORACE. So that has electroweak corrections and initial state corrections and interference, and it has multiple other aspects of the QED calculation built in. So just flashing a couple of distributions about the photon energy, the number of photons above some small threshold. The two calculations are very similar, but there is also quantitative information about exactly how much MW or MZ would be different. For example, if one tried one calculation against the other. So just listing the processes without going into details, the systematic uncertainty from potential variations in this part of the calculation, we estimate to be 3 million. Moving on to other production aspects. So first one is the transverse momentum of the W boson. So the first step is use the Z boson with the leptons. A very precise measurement can be performed. So this is the PT spectrum of the Z bosons first. And there are some parameters describing the non-perturbative physics at low PT, the perturbative hard gluon and hard quark radiation, let's say, at high PT. So these two parameters were fit. Some more information was taken from global fits, and you see the uncertainty that results. And we are able to get a pretty good distribution from Resbos for the Z boson spectrum. I'll come back to what happens with the W boson spectrum. There is a new part of the analysis which we never did before, which adds an additional constraint from the W boson PT spectrum as well. A cross-check that we didn't do in the past, but our colleagues have used it, so we decided to check this too. This is an angle between the two leptons. So back-to-back leptons in the Z's would be at 0, and highly boosted Z's would be in this tail when the leptons are not back-to-back. So this is a predictions, let's say, from our calculation, including detector effects as a cross-check, and that cross-check works well. Okay, so now we are at calibrating the momentum scale, specifically about, say, the magnetic field. And without reading this list, what we do in the calculation is propagate all the particles, electrons, muons, photons, through a highly granular map of all the material, the passive material in the detector, through the silicon sensors, through the COT, until you reach the calorimeter. And we published all the equations and how we do Compton scattering and photon conversion and so on. So this is all built in. Just an illustration of how that works. It's sort of like GEONT, except we want to do it much faster. So you take any particle of interest and step it through this fine-grained map, which is a few millimeters in each dimension. So it's a three-dimensional map in all three dimensions with a granularity of a few millimeters. So you just step through and execute the equations as GEONT would do, and then propagate the particles that come. Okay. Another just unrolled version of this high granularity map, material map, containing ionization energy loss information and radiation lengths and so forth. Momentum scale. Starting with the J size, so the statistics are so high that we can build J size in the relevant quantity that the tracker is measuring. So this is 1 over PT or curvature. So every one of these points bend along this axis, which is the relevant tracker axis. There is a fit like this, where the red line is the line shape calculated by the simulation. So from comparing to the known JSI mass, which is an extreme high precision measurement in the PDG, excuse me, one gets a correction for the, let's say, the magnetic field. And so every one of those corrections is plotted here. And this is one of the plots we stared at for a long time. The analytic study or the analytic expression that we are able to convince ourselves that is true results in the hypothesis that this plot must look like a straight line. So you can now tweak the slope of the line and the value, and that's how we are able to say that we have a momentum scale that fundamentally is independent of the muon curvature. But that is a statement that can be tested. So you can now go to the epsilons, and there are two ways of reconstructing the epsilons. One is with using the beam spot as a constraint, and one without. So this is an important cross-check, which we have always done. Let me just show for now that this cross-check works out very nicely. This is the beam constrained version of the same data. This is the non-beam constrained version of the same data. And apart from the significant improvement in resolution, which is why you include the beam constraint, especially for the high PT leptons, we are essentially now getting the same answer. This is one of the many things that improved the analysis, allowed us to get this precision. A table, I will just flash it, and it's sort of interesting to note that in the epsilon column, this is all parts per million precision from individual effects. So on the whole, a few tens of parts per million precision on the momentum scale. And it's sort of gratifying in a sense to see that on the epsilon column, the single largest contribution of systematic uncertainty is actually not from our experiment, but from the well-known, but the precision of the world average epsilon mass is actually now showing up in our column as the largest one. So interesting curiosity. Okay. So now we're ready to unblind the Z. So first with the muon channel, and this is the answer we got. So an independent measurement and confirmation of our momentum scale analysis comparing to the PDG value of the Z mass. Okay. Let's move on so we can make this plot now where all available information from J size, epsilon point, Z point, they're all independent of each other. We can take the appropriate average and get one momentum scale, which then applies to the W bosons. So this open square here or cross is not the measurement, it's the answer from the solid points, which are the measurements. EM calorimeter. So again, one wants to use fundamental knowledge of showering, which is nicely built into Géant, but it would be too slow by many, many orders of magnitude. So a separate standalone study was done and published where electrons and photons were thrown at Géant, and quantities like how much energy leaks out from the back of our calorimeter, including all knowledge of our calorimeter geometry. So that was separately published. And just an illustration that, for example, as you increase the energy of the electron, then the leakage fraction is growing. So as you can see, the leakage fraction is shifting to the right. So this and many other things were extracted out of Géant as parameterizations. Then they become inputs to our fast calculation. So this is another technique that has been used for decades. Simply plot the energy in the calorimeter divided by the track momentum for electrons from the W bosons and Z bosons, of course. So the peak allows you to constrain both the calibration, and the width allows you to constrain the resolution. This region here allows you to pin down the exact thickness of the calorimeter, so that affects the line shape. This region here, which is the radiative electrons, allows you to pin down exactly how much radiative material you have. So a few % correction was needed to our a priori map. And so this then goes back into computing the line shape over here. Okay. This is the same data but rebinned so that the fit to the tail can be done a little easier. So that gives you a small correction on the material amount in the detector. Okay. Non-linearity. So the calorimeter can, because of showering, can certainly have a logarithmic non-linearity at high momentum, high energy. So after including all the knowledge from Géant, potentially aging effects and so on can still induce some residual effect. So then the E over T fit is done exactly as you saw, but now in bins of transverse energy or transverse momentum. And so a small fitted parameter here makes sure that the data Z and W both are within uncertainties flat. And the systematic uncertainty is propagated from this. Okay. Another one plot which is describing spatial calibration. So this is now as a function of tower rapidity in absolute value. So central electrons and more forward electrons, same fits performed, and get it as close to 1 as you can, beyond which it doesn't matter. Okay. A cross check with the Z boson finally in the electron channel. So this is the unblinded number we obtained some time ago. We can now do the same cross check, as you can see, quite consistent. In splitting up the Z bosons, we start losing statistical precision, but it's a test one can do. For example, radiative and non-radiative electrons can be split off, and you can make subsample fits. Here is one of them. You can do that in using the calorimeter cluster, which is calibrated. You can do that directly with the tracks themselves, where the precision starts to suffer because the distribution is quite wide. But whatever statistical precision we have, you see that we do get consistency. Okay. Let me not spend much time on resolution. So you saw a lot of mass fits, a lot of peak distributions. So the width of those peaks, all of them are constraining the resolution, both of the tracking and the calorimeter. Okay. So now I should move on. Hadronic recoil model. This is where it's much more parametric because of all the soft pions and kaons and soft photons flying around. One thing before we enclose, before we put the PT balance information, is when the leptons go through the calorimeter, they also deposit some energy. That part has to be corrected for, otherwise it will be double counting. So this is very briefly a calorimeter map, let's say, folded out. This is the energies in the calorimeter towers, and you can see close to where the electron impacts or close to where the muon impacts, they are depositing some energy in the calorimeter. So that part has to be cut out in the calculation of the hadronic recoil. Whatever is missing because of that cutout has to be corrected for, and these are distributions, data, and Redis simulations showing how that cutout energy is changing as a function of various kinematic quantities. Model is describing the data well. So now we can go very quickly through the PT balance. This is the response on average in the calorimeter to that inclusive shower of soft particles. Many of them don't even reach the calorimeter, so the response is clearly less than 1. But as you increase the momentum of the boson, then more and more reaches the calorimeter and many other effects in here. So this is a parametric response, which we get from the data. Let me see if I can wrap up in a few more minutes. Without going into details of every plot, you will see the intent here is just to see how well the tuning plots are able to get the simulation to look like the data in the average value of the response, in the resolution of the response, in the resolution in the other direction, so perpendicular to the boson direction, understandable effects as to why the response, the resolution is growing there. More distributions looking at the azimuthal phi smearing of the hadronic recoil. So these are all the particles recoiling against the boson. How back-to-back are the two vectors. 0 means they're back-to-back. So this is all the resolution smearing. And as you change the PT, there is more collimation. Bottom line is these are tuning plots that are working well. With a few parameters, we are able to describe entire distributions. Same logic here. With a few parameters, we are able to describe a lot of distributions. So these are now histograms of that recoil quantity. More histograms of the recoil quantity. I should say, whenever I say new, we say new, a lot of detailed comparisons, which we didn't do in our previous papers, are being done this time. This is not tuning plots, so these are check plots, predictions, shall we say, of the simulation. This time looking at the Ws. So projections of the energy in the W events parallel and perpendicular to the lepton, muon, and electron channel. So let's leave the slides there. One more aspect worth emphasizing is it was always an assumption in the past that the W boson PT spectrum is a prediction given that you pin down the Z. But this time, check that prediction carefully with another program completely independent. And we use the W boson spectrum directly as a data constraint on this. And it turns out that ResBos is working well. So we checked how well this works, and no additional tuning on ResBos was actually needed. We are just able to quantify the constraint from the data this time. Okay. One more slide on PDFs. Perhaps we can just look at all the checks that we did, comparing various PDFs, NNPDF as the central one, but small variations with the others. As another check, we use NLO PDFs, not for the central value, but again, checking for sort of internal consistency. And so it seems like a robust estimate of PDF uncertainty. And without reading the slide, just describing various sources of backgrounds. If time allows, we can come back to this. I would just flash the background fractions and including also the uncertainties in the distribution shapes, not just the normalization. Most of the time, there are small systematics. Occasionally, you will see 5 MeV level systematics arising. Okay, so with that, we already talked about the blinding, so I'd like to wrap up. Let's just flash the transverse mass fits here from the two channels. The bottom plot will be the residual. The blue points are the data minus the best fit simulation. So generally some scatter, but no systematic trend. Same for the PT of the lepton without using any hadronic recoil information. Same for the worst, the most sensitive to systematics, let's say, which is the inferred neutrino transverse momentum. And you can have a look. Okay. The 6 numbers from each individual fit with individual statistical and systematic uncertainties with the correlations that are well known by us here. We can make a best linear unbiased estimator combination of all of them, and that results in the answer that was published. Separate subsample fits, instead of including all 6 fits, you can take whatever combinations of them just to check internal consistency again. And that gives some confidence if you look at the statistical chi-square of picking any 2 or 4 or 6 of them. So combined electron, combined muon, fairly consistent, and again, the bottom line answer. Okay, we flashed this plot before, so I'll just now flash quickly the corresponding new plot, new table, and maybe we can take 2 seconds to just see how those individual numbers evolved, and then move on. Detailed table, let's leave it here in the slides, and maybe I'll flash this one. This is the corresponding table on that final answer, which is the combination of the 6 fits. This is what we had 10 years ago, and this is what it looks like now. So one could again flip back and forth once or twice, and then move on. So this is figure 1 from the paper. And this is figure 5 from the paper. And we want to acknowledge that after our paper was submitted and accepted, the LHCb paper was also accepted and published. So at the time we submitted the paper, the LHCb number we thought is prudent not to include, not yet published. But we want to acknowledge that that publication has come out, very nice. And so now we will show that number here whenever we show this plot. Okay. And let me wrap up here. So here is some information we can come back to about all the changes that were done in the analysis, substantially new version of the analysis this time compared to 2012. So with that, thank you for your attention and this opportunity to show you briefly how the measurement was performed and what answer we got. And here are the numbers, the standard model expectation and our measurement. And without reading, this is the last few statements we make in our paper. So again, thank you for your attention.
Thank you very much, Ashutosh. Thank you. Thank you for the nice presentation and on this very important result. And once again, we would like to congratulate the CDF calibration to reach this precision measurement. So before we open the floor for the Q&A, we have 4 more CDF colleagues on the panel. I would like to ask them to give a few very brief remarks. So each one of you be limited for 1 minute. So Giorgio and David as the co-spokespersons, and Christopher as the electric physics coordinator, and Bo as a primary contributor to the analysis. So Giorgio, would you like to go first?
Okay, thanks. Thanks, Aman. I'd like to stress that one point. CDF collaboration has done a lot of work over the years. We have been well known for our procedures and the tight review, the internal review that we did. And I want to stress that what we have done here is even better somehow of what we did in the past. There was an extra effort because we knew this was a heritage measurement. Of course, we didn't know how the outcome would have been, but we put a set of excellent reviewers. I'd like to thank here. Several of them were former CDF spokesperson, and they've done a great job in looking through all the analysis over and over again. And that's, I think that the integrity of the process was something which we concentrated to keep the analysis focuses and to keep everything under control.
Thank you, Giorgio. David, please.
Gee, Giorgio just said everything I wanted to say. He's right. You know, people have thought that CDF has been dead for many years, and we haven't. We've just been very quiet. We needed to be left alone to be able to do this thoughtfully, carefully. The dominant issue to us was avoiding bias, which we did with the unblinding procedure. And it was really about being able to put the stamp of CDF approval that people have come to rely on over many decades. And this has surely earned it. The level of scrutiny, as Giorgio said, certainly rivaled that of the top bar procedures with the blinding, were far more stringent. We're incredibly proud that our our colleagues decided to stay the course because we knew this was so important. And we're just very grateful to be able to share the facts as we know them today with the world.
Thank you very much. Of course, we see CDF is certainly survived for the COVID. So I don't see Christopher. Is Christopher connected?
Yes.
Yeah, please, go ahead, Christopher.
Right. So, so just to say, I was one of the co-authors, and Bo was the lecture convener for the experiment. So I would, so as a co-author, I would just maybe highlight a few things that Ashutosh has said. I mean, maybe actually some of the things that he skipped over. He pointed out the importance of the alignment procedure, which is a starting point for this. For the tracking momentum measurement and the importance of getting a uniform set of tracks in reconstruction. And one thing that doesn't come through fully, I think, in the papers, the same kinds of procedures were applied to the calorimeter, where we did a lot of work to get uniform response to the electrons and also to the recoil. So there were corrections dedicated to the response and the data to achieve uniformity throughout the whole measurement. So he gave a flavor with the alignment, but this was done throughout, and we didn't have space, I think, to put everything in there, but that's summarized in one of those tables. So I just maybe point that out.
Okay, thank you. Bo?
Yeah, so as Chris said, I'm actually the lecture reconvener for the duration of this analysis. I was one of the primary authors in the previous WMAS measurements, so I've seen this from both sides, and I know how much work goes into it and how much work Ashutosh and Chris have put in for the past decade. So just to echo what Giorgio and Dave said, the level of scrutiny and review on this analysis has been immense, and in part because it's taken longer, collaborators have had more time to add their feedback and input and really carefully do a read of everything that the analyzers have put out. And so it really, in some sense, didn't suffer because of the lower level of overall engagement and collaboration, because of the interest on this measurement. And finally, just to add, a lot of people have asked how we kept this secret, because we did unblind November of 2020. And let me tell you, COVID helps you keep a poker face because we don't see anyone. And so it's been easier to keep that a secret as a result.
Thank you very much all. So let's open the Q&A session. So we would like to start from the remote questions, and my co-chair, Andre, would monitor the questions.
Okay, so we have, can you hear me okay? I'll presume the answer is yes. Okay, yes. So we have 3 questions online. They're kind of technical, so if you can keep the answers relatively brief, that would be great, so that we can give people on the floor a chance to ask a question as well. So the first question is, can possible mismodeling of PT recoil, especially a small inaccuracy in implementation of angular correlations in the resummation program RESBOS, explain the CDF measurement?
We don't think so.
Okay. And the other question is about the...
Yes.
That's good. The other question is about the PDF uncertainties. They went down from 10 MeV to 3.9 MeV. Does this reflect an improvement in the PDFs or a change in the data analysis strategy?
The first thing you said.
Okay.
Yeah.
Excellent. So then there's a third question, which is, this result differs significantly from other previous measurements. How do you explain this difference? So there are 2 hypotheses here. Is this a systematic effect in this or the other experiments, or some difference in the physics that might be impacting the 2 measurements in some, or your measurement versus all the other measurements in some way?
I'll make 2 brief comments. One is, we do put a lot of effort in demonstrating the single most important aspect, which is the momentum scale. So you saw how we treat that fundamentally, and we use the Z bosons as a crucial proof of that. There are, of course, well-known differences between the production processes at the Tevatron versus the NHC. This is going to be a continuing investigation. Historically, the program that we have used has been able to describe the production of W bosons and Z bosons at the LHC very well. Things are more complicated at the LHC because of the PP process, more contributions from the C quarks and gluons. This can, of course, also be understood well, but that conversation now can happen. Spokespeople mentioned that we wanted to be very careful about bias. We want to be independent. This is the time that now we can share all these common correlation issues. But during the process of analysis, we were in fact trying to focus and remain as independent as possible. It's crucial in our field that the independence between different measurements is maintained.
Okay, so there's one last online question which has to do with the standard model prediction. And the question is, can that improve? Is that expected to improve in the near future for the electroweak fit?
This is where maybe colleagues, our experts in the audience even here may have input and will have input. Let me just throw out one thought that a colleague mentioned, which is, in addition to the electroweak physics that's in here, is the QCD condensate that we know also exists from the QCD side, the QQ bar condensate. Are the effects of that included in here? I have no idea. So these are the sort of things that we would love for our theory colleagues to be looking into.
Given the interest of time, I think we should ask questions from our audience here. So anyone has a question, please proceed to the microphone in the central lane. Yes, please.
Thank you for the nice talk. I didn't see the samples separated by charge in either lepton by charge in terms of, and also the angular distribution. Have you broken up the MW prediction by either pseudo-rapidity or azimuth?
So here you see table S10 from the paper. This shows L plus and L minus, so muon and electron channel. I think that was your first question, charge dependence. The next was separation by pseudo-rapidity and azimuth. So here is the azimuth. We
don't see it. Yeah.
Could you share, screen share?
I should be screen sharing because it's telling me stop share, so I am sharing.
You see it on Zoom. Maybe you could stop and start again, perhaps.
No, but we can see it now.
Okay, you can see it now. So here is the table S10 from the paper. You see the first question you asked was charge separation, so there it is for the two channels, first line. You said azimuth. Here is one way of separating the azimuth. We can do it more finely, but here we have one separation. Rapidity, what we have is a very careful model of the acceptance and reproduction of the azimuth of the pseudo-rapidity distribution. Our pseudo-rapidity spectrum is only plus or minus 1 or absolute value of 1. So that we have not separated. And the reason, of course, is that the analysis was designed as an inclusive analysis. As Chris mentioned, we have made more and more efforts, including many other things, to do run dependence, calibration of the tracker, of the EM calorimeter, and there would be more enlargements of the infrastructure would be needed to be able to divide into more things like time slices or rapidity slices. So that functionality at the moment doesn't exist. And to do it, we have to do it right. So, some slap together kind of cross-check would not help anybody. So this is what we have. More things, ideas have accumulated, exactly like you said. So we'll go back to the drawing board at some point and think about how you would, if you could change the analysis to become semi-automated in all the subsamples. Otherwise, it requires essentially, repeated brute force analysis of every subsample one at a time. And you could count the years for that.
Okay, thanks. Any further questions? Gordon?
Hi, this is Gordon from the University of Washington. First, it's great to see all of you again. Second, congratulations. I know how much this must have taken. I did some work on the WMAS towards the end of my D0 career, so it's really fantastic to see this. I just had one question. The new PDFs that you used, did they shift the central value or just reduce the error? And do you understand that, or I'm guessing there's an answer coming.
Let me get to the slide. It's on the slide. Where is that slide? The shift is small, so here is the documented shift.
Great.
There you go. Is that the slide we want? No, sorry, wrong slide. There's a 3.5 MeV shift from the PDF we used before to one of the modern PDFs we are using now. Plus 3.5 MeV shift because of the switch to this. We used to have a 10 MeV systematic uncertainty from the old PDF. The shift is 3.5 MeV. The new uncertainty is 4 MeV. So you see the compatibility of those numbers.
Okay, great. Is this, so I looked at the paper. I did not see this information in the paper. Is it in the, maybe I missed it, or is it in the supplemental?
It's all there. Everything here is there.
Okay,
and more.
I just missed it in the paper. All right, thank you.
I would like to take the opportunity being a chair to ask a question. I don't know whether my co-chair would agree with me. Anyway, let me ask you this question, Ashutosh. So we know that there are two critical quantities to come into the transverse mass fit. One is the transverse motion of the W boson, and that's a critically important, has been discussed, and you calibrate this against the Z. It's a great job. The other parameter to come in is W width. W width is not known very well. W width has an error bar 42 MeV. My question is, how do you model the W width?
We use the standard model calculation. So for a particular W mass, one has a particular standard model calculation. We have chosen for the time being the standard model width calculation from the PDG.
But did you modularize this width as a free parameter in the fit, or you fixed the width?
Historically, it was done as a free parameter. It makes absolutely no difference. So we can show you in one of our publications what the mapping is from a particular gamma to a particular MW. Right? So there's a correspondence experimentally from if you change the width by some amount, how much does MW change? So we can all pull out a pencil and paper and say, if you were to change the width by a different standard model calculation for a particular MW and then use that map, how much would the MW change from the analysis? The whole effect is negligible.
Okay, thank you. Any other further questions? Yes, please.
Hello, Felipe from University of Madrid. I was asking myself, how can you undercut Atlas in the statistical uncertainty?
Undercut Atlas. There is a significant boost. So I'm thinking on my feet here. There is a significant boost to the W bosons produced at the LHC. So the Jacobian edge, because of that boost, is not as sharp as it is at the Tevatron. There is much more QCD, in other words, at the LHC. You can see this from the fact that when we require the boost to be small, which at the experimental level is 15 GeV is the requirement we make, the corresponding requirement in the Atlas analysis is 30. In other words, because the Ws are so much more boosted in the transverse direction, you have to allow a bigger phase space. And so that smears out the Jacobian edge. This, and every factor of 2 in smearing is a factor of 4 in statistical power. So this is probably one of the large contributors to the Ws being a little more at rest in the Tevatron than the LHC, helping to narrow up the distribution.
Okay, thanks. I think we're running short of time. We have another session to go. Maybe we can ask for the one last question. Yes, please.
Hi there, this is Dave Herzog from University of Washington. I'm a G-2 person, so I don't know too much about all your cuts. I was completely struck by this alignment to a micron of a device that large with such, that's beyond imagination, such a small thing. And I'm curious, you've taken data over presumably many, many, many years, and the mechanical thing staying stable or understood to that level strikes me as, was there a plot of your result as a function of time, just so that we could see if there was any edge, any breathing or shaking of the device over time?
The drift chamber alignment was done in slices of time, so there is an independent paper on that. Secondly, the single largest effect is that the whole chamber drifts up and down as opposed to internal deformations. So that was done consistently over run by run almost. So I think that dedicated paper has some plots in it. But indeed, the entire positioning of the drift chamber over 10 years was constantly readjusted so that it was centered on the beamline, carefully done with collider data. One last thing as a cross-check, maybe we flash, if I can get these things to move, take the run dependence of the momentum scale as an ultimate check. So if I can get to it quickly, look at the Z mass as a function of time, look at the epsilon mass as a function of time, as a function of instantaneous luminosity. Here, we have this plot up. So Z mass in the two channels as a function of time. So alignment is crucial in the muon channel here. You can see the statistical uncertainty on this. You can look at the epsilons down here again as a function of time, early half versus latter half.
Thank you. I think our time is up. I would like to conclude the session by thanking our CDF colleagues again, and thank you all for the participation. Thank you.
Thank you.